In this next topic, we're going to continue some calculations with limiting reactants and limiting reagents. For this next practice problem, we are told that octane reacts with O2 gas to produce CO2 gas and water. Suppose 88 grams of octane is mixed with 98.6 grams of O2. Then we're going to calculate the minimum amount of octane in grams that could be left over after this reaction takes place. So this is the chemical formula for octane. Here's oxygen, carbon dioxide, and water. This equation is not yet balanced, so let's figure out how many carbons are on both sides first. So here's 1, then 7 total, then 8. So we have 8 over here, 1 over here, so we can add in this 8. Hydrogen, we have 3, then 12, so 15, plus another 3, that's 18. Here we only have 2, so now we can add in a 9 here, so we have 18 hydrogens here and 18 here. For oxygen, the tricky one, we have 16 and we have 9. So 16 plus 9, that's 25. There is no oxygen here, so we just focus on this coefficient. So we take the larger value, 25, over the current amount, there's 2. So now this is our new coefficient. It's a fraction. How do we get this number out of a fraction? We can multiply it by 2 to just get 25. That means we need to multiply this equation times 2. So 2 all the way through to all these coefficients. When we do so, we'll get a 2 here. 2 times 25 over 2 is just 25. 2 times 8 is 16. 2 times 9 then is 18. This is our complete balanced equation. Again, you should know the formula for oxygen. Remember, it's a diatomic, carbon dioxide, and water. You do not need to be able to recognize that this is octane. Okay, so you should be able to take a reaction written out though and be able to balance it like this. So we balance the reaction. Next, we know we need to eventually go into moles. For octane, we start out at 88 grams. You can calculate its molecular mass with all the carbons and hydrogens, comes out to about 114. So we take 114.2285 grams per mole of octane. That gets us 0.7704 moles of octane. We're just focused on the octane and the oxygen from the question we were asked. So now we can look at oxygen as well. We were told it started out at 98.6 grams. The molar mass of oxygen is 32 because there are 2 oxygens. So O2 is a diatomic, so technically the molar mass of oxygen is 16 times 2. So the atomic mass of oxygen times 2. Because this is diatomic oxygen, so that molar mass is about 32. So 98.6 grams of oxygen. Here is the molar mass of oxygen. So grams cancels out, leaving just moles of O2. That comes out to 3.0814 moles of O2. So now we balance the reaction and we figured out the starting amount, but not in grams, right? Because we always want to work in moles. We at least always want to start working in moles. Then if we need grams, we can convert from moles back to grams. Let's first assume that octane is our limiting reactant. We're starting with 0.7704 moles of octane. We need the very important mole-to-mole ratio of octane to oxygen. For every 2 moles of octane, we're going to need 25 moles of O2. So here's octane. We need to put moles of octane in the denominator. So we know from the balanced reaction, 2 moles of octane for every 25 moles of O2. So octane and octane cancel out, leaving just moles of O2. That comes out to 9.630 moles of O2. Did we start with this much? Do we have this much oxygen to use? If we have this much octane we're starting with, and this is our mole to mole ratio. Well, here for oxygen, we only have about 3 moles of it. So we don't have 9.6 moles. At this point, we can say with certainty that octane is not the limiting reactant. Right? We don't have this many moles of oxygen when there's only about 3 moles to start with. Well, let's then prove that oxygen really is limiting. So we know we started with about 3 moles of oxygen. So 3.0814 moles of oxygen with this mole to mole ratio between oxygen and octane. So for every 25 moles of O2, we have 2 moles of octane. From the mole to mole ratio of that balanced chemical equation, moles of O2, moles of O2, these cancel out, leaving just moles of octane. This equals about 0.24651 moles of octane. So with this starting amount of moles of oxygen, we only need 0.24651 moles of octane based on this mole to mole ratio. Did we start with this many? Yes, right? So we started with 0.7704 moles of octane. So we're going to have some octane left over when all the oxygen reacts. So oxygen is definitely our limiting reactant here. Okay, so we figured that out from trial and error. So assuming octane was limiting, then assuming oxygen was limiting. Now, because oxygen is limiting, now we can solve our problem. So let's figure out the moles that are used up here. For oxygen, we start with 3.0814. We're going to use all those moles up. When we start with this many moles of oxygen, we're going to need 0.24651 moles of octane. So we started with this many moles of octane. We started with this many moles of O2. To fully react our limiting reactant of O2, we end up needing to use up 0.2641 moles of octane, and we started with 0.7704. So taking this amount minus this amount means we have this much octane remaining, but importantly, it's still in units of moles. So we have this much remaining, and we were asked about the gram amount of octane remaining. To go from moles to grams, we can use the molar mass of octane. So this many moles of octane, we have the molar mass that we calculated previously. So grams per mole of octane, moles cancels out, we're left with just 59.84 grams. Then to get this into the correct number of sig figs, we round 59.84 grams of octane to 60 grams of octane. We do importantly need that decimal point here because just writing out 60 means we just have 1 sig fig. Adding this decimal here means we have 2 sig figs. And we want 2 sig figs in the end. The next topic here is understanding theoretical, actual, and percent yield. To define these, the theoretical yield is the amount of product that would result if all of the limiting reactant was reacted. So that's theoretically speaking. The actual yield is the amount of product actually obtained from a reaction in the physical lab, for example. Percent yield, then, we're making a comparison between how much should have been produced and how much was actually produced to get percent yield, so actual yield divided by theoretical yield times 100%. Okay, so we're comparing the actual yield versus our theoretical yield and reporting it in this percent yield. So we end up multiplying by 100%. In this practice problem, we have compound A combines with compound B to produce compound C. we have some information about the initial amount of A and B and the final amount of A and B. It looks like we started with 3.5 grams of A, and at the end, all of that was used up. We started with 9.0 grams of B, and at the end, we still had 6.0 grams remaining. From looking at this information, it's clear that A is our limiting reactant. So from this information, we're going to calculate the theoretical yield of C, and then suppose that the percent yield of C in the reaction was 40%, to then calculate the actual amount of C that was isolated at the end of this reaction. So here's these definitions again of theoretical, actual, and percent yield. So to reiterate these definitions, the theoretical yield is the amount of some desired product that would be produced if every possible atom of the reactants were consumed and they turned into the product. That is taking into account the limiting reactant though. The actual yield is how much of the desired product was actually isolated after the reaction. The actual yield is always going to be less than your theoretical yield. The percent yield is the actual yield divided by the theoretical yield. So if the actual yield were half of the theoretical yield, for example, the percent yield would be 50%. Let's say we made 1 gram in the lab, but theoretically we should have made 2 grams. So 0.5 times 100%, that would be a 50% yield. Now, to solve our problem with A and B, we don't have a chemical equation and we don't have any chemical formulas, but we keep in mind this idea of the conservation of mass, which tells us that the mass of the reactants that disappear must equal the mass of the product. So anything consumed here must be formed into our product, or C. So whatever's consumed from A and B had to produce our product C because nothing else is produced here, is what we're told in the problem. So for the theoretical yield of C, that's how much we get when none of the mass of the reactants ends up lost or in any unwanted byproducts. So anything used up from A and B goes into C, and everything used up in A and B will go into C. So that's our theoretical yield, how much we should get of C if all amount of A that's consumed and all amount of B that's consumed goes into forming C. So we know right off the bat that all of A is consumed. For A, all 3.5 grams of A went in to produce this product C. So now to find the mass of B that's consumed, we started out at 9.0 grams, and we were told that 6.0 remain. So then we're using up 3.0 grams of B to produce this product C. Now in this next step, we're using up 3.0 grams of B and 3.5 grams of A. That means that our product C has to weigh 6.5 grams. Theoretically, right? So if all of A and all of B go in to produce product C in a perfect reaction, then we have to have 6.5 grams of C in the end. So our theoretical yield of C is what we're going for. Theoretically then, that's how many grams of C would be produced if all of A and all of B went into perfectly formed product C. We had a perfect mass transfer of A and B, so from one beaker or one container to the next, all of this of A and all of this of B go into theoretically produce 6.5 grams of C. So 6.5 grams of C. Now for this next step, we're bringing this idea of a 40% yield. So now we have a 40% yield. This equals our actual yield over our theoretical yield times 100%. We just figured out this theoretical yield of C, so we can plug in 6.5 grams here to isolate just our actual yield. So 40% divided by 100, that's 0.40, That's going to equal our actual yield over 65 grams, our theoretical yield. So then 0.40 times 65 grams is our actual yield. This should be 6.5 grams. So 0.4 times 6.5 grams is 2.60 grams for our actual yield of product C. We got that because we were told this 40% yield happened in the reaction. So we knew theoretically how much should form, so 6.5, but only 40% of that actually was yielded in the real lab. So that 40% of 6.5 is 2.6 grams of C. So we get this answer, so 40% of 6.5 grams, 2.6 grams. Here are our final answers here for the theoretical yield and then the actual yield. Next, we're going to go into the theoretical yield of chemical reactions. So not just hypothetical A, B, and C, but using real chemical reactions. We have aqueous hydrochloric acid reacts with solid sodium hydroxide to produce aqueous sodium chloride and liquid water. What is the theoretical yield of water formed from the reaction of 1.8 grams of hydrochloric acid and 1.0 grams of sodium hydroxide? Notice we're given an amount of hydrochloric acid and sodium hydroxide. So because we're given two of these amounts, we know we're going to be working with a limiting reactant style problem. So we're told hydrochloric acid and sodium hydroxide react to form aqueous sodium chloride and water. You should recognize sodium hydroxide as a name, water, as well as sodium chloride. This is an acid, and we'll cover more acids in Chapter 4. So recall the theoretical yield of water is the maximum amount possible of water that the reaction can produce. The most water the reaction can produce is the amount of it produced when all of a limiting reactant is used up. So either all HCl is used up or all of NaOH is used up to produce the maximum amount of water as a product. So in solving this, we do need to figure out what's our limiting reactant first. We do need to calculate the molar masses, so HCl comes out to 36.461 grams per mole, sodium, oxygen, and hydrogen, or sodium hydroxide, about 40 grams per mole. So we're given these gram amounts of hydrochloric acid and sodium hydroxide. We first want to convert those into moles. Let's first assume that all of the HCl or hydrochloric acid is used up. That means we're starting with 0.04937 moles of HCl. Really importantly, what we need here is these mole to mole ratios. So for every 1 mole of HCl, we have 1 mole of NaOH. So for every 1 mole of HCl, we have 1 mole of NaOH. That means we're going to need 0.04937 moles of NaOH for every 0.04937 moles of HCl. Do we have that much that we started with? We only have 0.025 moles of NaOH. We got that amount from this starting amount of 1.0 grams of NaOH. That means the HCl is not limiting, right? We didn't have enough NaOH to match this amount of HCl. So HCl is not limiting. It means that sodium hydroxide is limiting. So again, because this reaction can't use up 0.04937 moles of sodium hydroxide, because there are only 0.0250 moles of sodium hydroxide to begin with. It must be that the reaction would run out of sodium hydroxide first before all the HCl is used up, meaning definitely that sodium hydroxide then is our limiting reactant. Okay, so we had a balanced reaction. We have this as a balanced reaction. I didn't prove this is balanced, but we have one Na, one Cl, one Cl, hydrogen, 1 and 2. Here's 2, oxygen, 1 and 1. So this is a balanced reaction. So we first balanced that reaction, then we took the gram amounts into moles. So we took these gram amounts into moles, then we figured out which one is our limiting reactant while working in moles. So let's prove that NaOH is definitely the limiting reactant, just to be safe. We are starting with 0.02500 moles of NaOH. For every 1 mole of NaOH, there is 1 mole of HCl. So moles of NaOH cancel, leaving just moles of HCl. So 0.02500 moles of HCl. Did we start with this amount or more? Yes, we started with 0.0497 moles of HCl, again, from this mass amount here, so 1.8 grams of HCl. 1.8 grams of HCl is this many moles of HCl. So we're not going to run out of HCl before we run out of NaOH, meaning that we did prove that NaOH is our limiting reactant. Sodium hydroxide is our limiting reactant. So we proved this here. Now we can continue on with the problem. So we're going to calculate the amount of water that would be produced if all of that limiting reactant is used up. We know we'll have plenty of HCl, but we know that sodium hydroxide will dictate how much water can be produced. That's why we only need to focus now on the NaOH, our limiting reactant. We know we started with this amount of NaOH. Now we need a mole-to-mole ratio to connect NaOH to water. Going back to our balanced reaction, for every 1 mole of NaOH, our limiting reactant, we have 1 mole of water. So now we can use this conversion factor in our problem. For every 1 mole of NaOH, 1 mole of water will be produced. That means we'll have 0.02500 moles of H2O that are produced. That's if all of the sodium hydroxide were used up because it's our limiting reactant here. We're asked in the problem to report mass of water, not moles of water, so we do need to convert this into mass using the molar mass of water. So about 18 grams per mole. That means we're going to have 0.4504 grams of H2O produced here. And we used up all of the NaOH. We used up all of the sodium hydroxide, our limiting reactant, to form this many grams of water. To get this into 2 sig figs then, we round to 0.45 grams. So that is our final answer. 0.45 grams of water is our theoretical yield of water produced from this reaction. Again, if all of our limiting reactant is used up. Next, we're going to do percent yield of chemical reactions. I also, again, want to point out some more practice problems here in the main slide deck. We're going to solve this problem where we have octane reacts with O2 to produce CO2 and water. We have this many grams of CO2 is produced from a reaction of 99.38 grams of octane and 567.2 grams of oxygen gas. We're going to calculate the percent yield of CO2, and I'm going to do this in a little bit different of a way. So I'm going to use this technique called setting up a rice table. You may have heard this called an ICE table as well. So how we've done the problem so far is totally fine. I am going to show you this, one of these methods. I call it the rice table. If you like this method, feel free to use this one as well. Figure out a way that you feel comfortable solving this style of problem. The very first thing we need to do, either way, is to set up this balanced reaction. So here's octane, here's oxygen gas, carbon dioxide, and water. We balanced similar equations like this previously in chapter 3b. So feel free to go back in the recording to see how we'd balance a more complex reaction like this. So we ultimately want to calculate the percent yield of CO2. To calculate the percent yield, we know we have 85.8 grams of carbon dioxide that are produced from this reaction. That is the actual amount of CO2 that was produced in the reaction. We do not yet know this theoretical amount that could be produced from the reactants that we have and from the amount of the reactants that we have. So 99.38 grams of octane and 567.2 grams of oxygen gas. So we need this value here to solve for the percent yield. So this theoretical yield is the maximum possible amount of CO2 that can be produced from the reaction. This amount will be dictated by the limiting reactant being fully used up. It has to be fully used up to produce the maximum possible amount of carbon dioxide here. In using the Rice method, we still are going to need this balanced chemical reaction as well as the molar masses of octane and oxygen. In the Rice method, we have R, the balanced reaction, so R for reaction, I for the initial amount of moles, again, always working in moles, C for the change in moles, E for the n number of moles at the end of the reaction. So we have R right now, we have the balanced chemical reaction. Note these subscripts here. I is the initial amount of moles. For a limiting reactant problem, we're really only concerned with finding out, is this a limiting reactant or is this the limiting reactant? So we're told the initial amount of moles of both of these through the amount of grams that are present. So we have the gram amount, but we need to convert these into moles because we need the initial amount of moles. Let's start out with 99.38 grams of octane. Octane has this molar mass, so to leave just moles, we would put 114.2285 grams in the denominator per mole of octane. This comes out to 0.870011 moles of octane. So with this starting amount of moles of octane, we can put this into the Rice table. So 0.87 moles of octane. For oxygen, we have 567.2 grams of oxygen gas. Remember, oxygen gas is diatomic, so its molar mass is about 32. So grams in the denominator, moles here in the numerator. This gets us about 17.72 moles of oxygen. So initially, we have this many moles of octane, this many moles of oxygen. Technically, if we want to write in the reactants as well, the reaction hasn't started, right? So initially there are no moles of CO2. I'm sorry for that. I did not put CO2 here. So the balanced reaction is CO2 here. So there's initially no moles of CO2. There's no moles of O2. So initially there's 0 moles of CO2 and 0 moles of water. That is the I step in this Rice table. Next, then, for the change. For the change here, we're ultimately wanting to find out how much CO2 there is that's produced. To do that, we need to find the limiting reactant. To find the limiting reactant, we're either going to assume that all the octane was used up or all the oxygen was used up. So to determine the limiting reactant, we're going to figure out which one is used up. To set up this change part, we're going to take the molar coefficient here and assign an arbitrary variable here. Then for oxygen, we're taking minus this coefficient here, so 25. We'll assign it a different variable. So this coefficient goes here, this coefficient goes here. So which one is the limiting reactant? It's going to be the one with the smaller variable. Let me show you what I mean. If we're assuming that all the octane is used up, we'll end up with 0 in the end. To solve for this variable x, we're going to take 0.87 moles of octane initially, minus 2x equals 0. Solve for x. So 0.87 minus 2x equals 0. X here for octane is 0.435. Let's try this with oxygen now. We're taking 17.72 moles, the initial amount. The change is minus because it's losing some amount of moles. It's losing some amount to produce these products. If this is a limiting reactant, it's going to also end up with 0. So to solve for y now, and I just arbitrarily assigned x and y. You can use whatever variables you want here. So 17.72 moles of oxygen minus 25 times y equals 0. We would subtract 17.72 from both sides, then divide by 25 to solve for y. The y value here is 0.7088. Using this Rice table, then our limiting reactant is the one with the smaller variable. 0.435 is the smaller variable. This one is associated with octane. This means that octane is our limiting reactant. You don't have to use these Rice tables. This is just one somewhat more straightforward way to do it. If you like the guess and check method as well, that's totally fine. I just wanted to present this alternative way for you as well. So this is called a Rice table or a reaction table or an ice table. So if octane is our limiting reactant, now we can move forward in actually getting the number of moles of carbon dioxide to then ultimately get our theoretical yield. With the theoretical yield, then we'll get the percent yield. So we're going to calculate the amount of CO2 that would be produced if all of the octane were used up. We know we started with this much octane, so 0.87 moles of octane. The mole-to-mole ratio of octane to CO2 is for every 2 moles of octane, there's 16 moles of CO2. Okay, so 2 and 16. So for every 2 moles of octane, 16 moles of CO2. Moles of octane cancels out, just moles of CO2. So then we get 6.96 moles of CO2 that can be produced from starting with this many moles of octane, our limiting reactant. Now we want the amount of grams of CO2, so we can use the molar mass of CO2. So about 44 grams per mole. This gives us 306.310 grams of CO2. Now we can plug that into our percent yield equation. So our actual yield, our theoretical yield times 100%. So our actual yield right here, our theoretical yield we just figured out on the last slide, then times 100%, then 28.0108%, and we put that into 3 sig figs. So our final answer is 28%. This is our percent yield of CO2. I'm going to add one animation here on limiting reagents or reactants at the end of this lecture. I also went ahead and included some additional slides on using the Rice table or ice table or the reaction table. So feel free to look through this example as well. And of course, as always, let me know if you have any questions. You don't have to use the Rice table. It's one way to approach those limiting reactant problems. Here's how we figure out this X and Y value. It's even a slightly simpler example than what we went through together. So here's an example of how we fill in this Rice table. Again, let me know if you have any questions at all. I hope you're all doing really well, and I will talk to you next time now for chapter 4. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Nitric oxide, NO, is produced when atmospheric nitrogen and oxygen react at high temperatures in an automobile engine. Once released into the atmosphere, nitric oxide is quickly oxidized to nitrogen dioxide, NO2. Nitrogen dioxide is a toxic brown gas. Much of the brown haze present in photochemical smog is due to the presence of nitrogen dioxide. The left side of the two-bulb vessel contains nitric oxide gas, NO, and the right side contains oxygen gas, O2. Click on one of the buttons to choose the number of molecules of NO you would like to react with the number of molecules of O2. Nitric oxide and oxygen gas are reacted in a 1-to-1 mole ratio. There are 4 molecules of NO in the left bulb and 4 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2 producing 2NO2. 4 molecules of NO are reacting with 4 molecules of O2. The 4 NO molecules require only 2 O2 molecules for reaction. Note the 2-to-1 mole ratio in the balanced equation. Therefore, 2 O2 molecules remain after reaction. The reaction stops once the nitric oxide gas runs out. NO limits the amount of product that can be formed and is therefore called the limiting reagent. Oxygen gas is present in excess. Nitric oxide and oxygen gas are reacted in a 2-to-1 mole ratio. There are 6 molecules of NO in the left bulb and 3 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 6 molecules of NO are reacting with 3 molecules of O2. They are reacting in a 2-to-1 mole ratio as represented in the balanced equation. No reactants remain after the complete reaction. Nitric oxide and oxygen gas are reacted in a 3-to-1 mole ratio. There are 6 molecules of NO in the left bulb and 2 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 2 molecules of O2 are reacting with 6 molecules of NO. The 2 molecules of O2 only require 4 molecules of NO for reaction. Note the 1-to-2 mole ratio in the balanced equation. Therefore, 2 NO molecules remain after the reaction. The reaction stops once the oxygen gas runs out. O2 limits the amount of product that can be formed and is therefore called the limiting reagent. Nitric oxide is present in excess.